All right, we're going to be looking at graph theory now, which deals with the concept of graphs. And in discrete math, when we talk about graphs, we're usually talking about structures like this that have a bunch of dots. We call these dots here either a vertex, or sometimes we call it a node. And those vertices and nodes could represent all kinds of things. They could represent actual computers in a network. This would be an example of a wheel architecture where you could have a bunch of computers all connected to each other and also some central hub of some sort. These also could be houses where there were wires running between them or roads connecting them. They could also end up being people who have interactions with each other or influence over each other. They could be species that compete in an ecosystem for the same resources. So what the graphs actually represent can determine all the applications of it, and graphs do have applications in many fields. The lines that are connecting the vertices together are called edges, and we'll define a graph by describing it as a set of vertices and a set of edges. Now, edges right now in these graphs, we call this an undirected graph. This vertex up here is connected to this one. The connection goes both ways. You can study, and we will, look at from time to time the idea of directed graphs, where you can only travel the graph in one direction. So when you start seeing arrows on the edges, that refers to a directed graph. But we're not going to deal with those mostly here. I do have an example here, though, of some other sort of more complicated but interesting applications of graphs. For example, this graph right here shows us actually Wikipedia editing languages. And the arrows show if essentially somebody has edited both an English Wikipedia page, and this would, I guess, be a Norwegian page. You can see here the Russian and Ukrainian, there's an arrow going in both directions. If we make this a little bit bigger, you can see that you have editors working on both of these. So Ukrainian and Russian have edited each other's pages. But this is more like a relationship graph, and it does have directions. You might have Hungarians have contributed to English, but not the other way around, and so on. So graphs, can represent sort of easier geographic or physical connections, but can also represent relationships. This example here is a Twitter hashtag network. So each of these, essentially, if you're following a follower, another user, or a hashtag, you have a edge connecting you, and you can see with the amount of connections you have that we have a much more complicated scenario than a simple graph over here. Now when you get to graphs this big, the analysis becomes much more complicated, and that's where graph theory gets interesting, and you need some pretty high level computers to kind of process this. But we're going to mostly focus on the concepts of this course, but in a computer science class you might deal with problems this large and have to come up with some algorithms to deal with that. Okay, so we're going to start at the beginning here with just basic graph terminology. Usually when we see an undirected graph like this, now this is a simple graph because we only have one edge connecting vertices. It's possible that you could have multiple edges. That would make you a multigraph. You could also have loops like this, which I actually might be wrong with that multigraph. I'll have to look that up again. But you can have also a pseudograph. This is called a pseudograph with a loop like this. And we'll see some of those. We'll work a few examples out so we can see the degrees of vertices. But the set of vertices here, we're going to use set notation. We're just going to say that the vertices in this graph are A, B, C, D, E, F, and G. And then the edges is actually going to be a set of sets. So we'll say that there's an edge from A to B. There's an edge from A to C. There's an edge from A to G. Right. And then there's an edge from B. We don't have to say B to A because we already have A to B covered, so we'll say there's an edge from B to F, and there's an edge from B to G. Now, as long as you get them all, because this is a set, it doesn't matter what order you do this in, but I'm going to try to do this in alphabetical order so that I don't miss anything. So C goes to D, and C goes to G. Who else do I have? From D, I need to go to C, but I already have that one, so I'll go from D to E, and then D to G, and then from E, I have to go from E to F, and E to G, and then from F I go to G. And this would be a description. This would be sort of a formal representation of this picture over here. Okay, these are the vertices, these are all the edges, and you would need something like this. Somehow maybe you'd use pointers or linked lists and programming to kind of model this graph so you could follow these paths. Now, one of the things we're going to talk about with graphs and vertices in particular is the degree of a vertex. The degree of a vertex for an undirected graph is the number of edges that are incident or coming out of that vertex. So let's start with the vertex A over here. If we look at the vertex A, there's 1, 2, 3 edges coming out of it. So the degree of A will be 3. If we take a look at the vertex B, right, we have 1, 2, 3 edges coming out of that. And if you take a look around at the vertices around the perimeter of this graph here, you can see that they're all going to be 3, right? C has 3 edges, D has 3 edges, E has 3 edges, F has 3 edges. But when we get to G, you can see here that G is actually connected to every other vertex, so we would have 6 edges. Okay. Now, one of the important theorems that deals with edges, if you take a look at the picture we have over here, you can see that the edge from A to B got counted towards A's degree, but it also got counted towards B's degree, right? Every edge, by definition, connects 2 vertices. So each edge is going to contribute to the total sum of the degrees by 2, right? This one edge right here between A and B bumped A's degree up by 1 and B's degree up by 1. Okay? The handshaking theorem says the sum of the degrees of all vertices in an undirected graph with m edges is 2m. That means that every edge contributes to the sum of the degrees twice. Okay? The reason we call it the handshaking theorem is if I'm shaking your hand, you're shaking my hand. Every handshake involves 2 people. Okay? Now, if you take a look at the number of edges, you could count the number of edges in a graph like this. It's small enough. We could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So we know that there are 12 edges here. Right? We could have also counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges here. Okay? But if we take a look at the degrees, 3, 6, 9, 12, 14, 12, 15, 18, 24, right? The sum of the degrees of all the vertices for V in V, uppercase V would be the set of vertices. This equals 24, right? That's 2m, right? 24 over 2 would equal the 12 edges. Okay. Now, once graphs start getting larger, sometimes when you try to count edges, you can get lost and wonder if you really counted that edge already. So sometimes it's easier to count the degrees, add them all up, and divide by 2. Now we're going to look here at another example of a more complicated graph where you have multiple edges and you have this loop over here. And make sure we understand how that's going to impact the degrees of all of the edges. So we'll start with the A, right? If we look at A, we can see there's just one edge coming out of that, so the degree of A would be 1. Now if we look at B, we'll do this one in green. B has 1, 2, 3, 4 edges coming out of it. Each of those count as a separate edge, even though all 3 of those paths connect B to C. Now you could think about this as maybe airline routes, right? We might have 3 different planes that connect B to C, and if you were trying to figure out how you could get from B to C, you could take any one of those 3 paths. You could also have different speed connections between computers. You could have maybe like a DSL and a cable line or other high-speed networks. So what the edges and graphs, edges and vertices really represent, it can change the application, but it's not going to change how we actually do the computations. Now when we get to C, you can see there's 1, 2, 3, 4, 5 edges coming out of C. Right? D, just like A, only has 1 edge out of it. The question really becomes, what about E? When we get to E, we can see that E has an edge connected to C. That counts as 1, but it also has an edge here that we call a loop. Right? And what we understood before is that every edge contributes twice to the sum of the degrees. Well, this loop is only attached to E, so it must increment E's degree by 2. So the degree of E is actually 3. Now if you add these all up, you can see 1, 4, 5, that's 10, 11, 3 is 14. The sum of the degrees, right, is 14. 14 over 2 equals 7, and if we were to count the edges, 1, 2, 3, 4, 5, 6, 7, we can see that this works. If you tried to make this a 2 instead, you would have had an odd number of degrees and the handshaking theorem would have been violated. Okay, so it can get a little bit tricky with the multiple edges, particularly the loops. You just have to remember that every loop is connected on both ends to the same degree, to the same vertex, so it's going to increment the degree by 2. Okay. Make sure you practice some of these. You should be able to get the hang of it pretty quickly. There may be some examples with directed graphs, and with directed graphs you have an in degree and an out degree, but that's not something we're going to get into at this point.